Hello students, so let us start our today's class on structure of atom. So if you were to look about the previous class, or we think about the previous class, so we have already started discussing about the atomic model. So far we have reached to Rutherford model, right? So we have seen at last that it has limitations. Okay, it has limitations, and further these limitations were encountered by this Bohr's model, which was a kind of a fabulous type of model that is prevailing till date. And various results means the main point of this atomic model is that it can go in hand with the current results that we get. Okay, many of the experimental data are in a good accordance with the data that are being given by the Bohr's model, and that is the beauty of Bohr's model. Okay, so for that reason he is very much appreciated, although it has some limitations. Okay, it has some limitations, but still with that point, from that point of view, in which it was just the starting for this model and all, he predicted a quite good model which proved many of the experimental data. So let us start with the Bohr model. Okay, so first of all, this is the model that is given by Bohr. So to say, this diagram is given here. Okay, so this model is especially for hydrogen-like species. So this is the most important thing about Bohr's model, that it is mainly dealing with hydrogen-like species. So why are we telling that hydrogen-like species and not all species? See, if you talk about the Bohr model, then it takes in information about the electric attraction between the nucleus, or you can simply say proton and the electron. That's it. But if you take a multi-electron system, means if you talk about hydrogen atom, it has one electron, one proton. So there is no electron-electron interaction. But as you move to higher and higher elements, the number of electron increases, and so the number of interaction increases, right? There are multiple electron-electron interaction, repulsions and all, and Niels Bohr did not account for that. So it was only applicable to hydrogen-like species. Now talking about hydrogen-like species, we have many other atoms which come under this category. Suppose we have helium atom. We have removed one electron from the shell and we got He+, right? Now He+ will have again one electron, then it will be also included in hydrogen-like species. Again, we can move to one more higher atomic number, that is lithium. It has 3 electrons. Just remove the 2 electrons, you got your hydrogen-like species. Now we are not talking here about the proton. We are only considering electron, because we don't have any kind of repulsion between the proton, or if there is, so there is not that much effect on the property. So the basic difference in the property is mainly due to the electron repulsion. So he said that Rutherford said that electrons are revolving, but he didn't tell us about that, where it will revolve, what will be the course of revolve, you can say what will be the course of choice, that where it will revolve. So we don't have any instructions for that, but Bohr gave that. Bohr said that there is only quantized states, okay, quantized energy levels or states or stationary states. You can say either of them. Okay, you can say either of them, means it can rotate in certain orbits only. Clear? And with certain angular momentum, means both of these things are quantized, means the energy is quantized, and if energy is quantized, then angular momentum must be quantized, because they are both are related. Clear? Okay, so this is the assumption here, that okay, electrons will revolve around the nucleus. So that is quite clear from the Rutherford only. But he said that okay, we will not just take any arbitrary rotation, or we will not take any arbitrary circular path. We will take quantized or specialized you can say orbit, which are called as stationary states or energy levels. Okay, you can say you can name it anything, and there the angular momentum is also quantized. So is this thing clear? So this is the basics of Bohr model for hydrogen atom. Now we will talk about the postulate. So the things which I have told, they are being postulated by Bohr, so I have taken from there. So the same thing is written, that okay, the electron will move around the nucleus, but it will do so in a fixed circular path of specific radii, and those circular paths or circular orbits whose radii is specified is called as stationary states or energy level. Clear? Now, these energy levels are such that even though the electrons revolve around the nucleus, they don't emit energy. So this is the very important point that deals with the drawback of the Rutherford. So Rutherford didn't say anything like this, that okay, that electrons are revolving, so since its velocity is changing because of the change in direction, so therefore the particle will continuously emit energy and it will decay. But he said that okay, what we will do is we will make some stationary states, and these stationary states are such that there will be no change in what? There will no change in energy with time. Clear? So due to that, they will not decay. Third postulate is about the transition. So we see that okay, that electron can transit from one stationary state to other. So they will do so. So from lower energy states to higher energy states and back to the lower energy state. Now this all transitions are defined with the help of what? With the help of electromagnetic radiation that they have consumed, and with the help of the difference between the energy states. So this thing is very important. So there is a difference. So suppose there is one stationary state, second is a stationary state, third stationary state. There will be the difference in energy. Now suppose we just radiate the atom with light. Now they will absorb electromagnetic radiation, or they will absorb light of certain frequency, such that the transition can be made. Okay, the transition can be made. It will be not, the energy will be not in such a way that electron will go in between those stationary states. Means it will take that absolute amount of energy which is only required to make that transition. Means suppose it will move from 1 to 2, or from 1 to 3, or from 1 to 5. It will make such transition. It will not go in between those. Clear? So that thing is mentioned only, that if you are moving from energy E1 to E2, then the frequency will be accordingly. Nu will be E2 minus E1, means the energy state, the final energy state, the energy of the final state minus the energy of the initial state divided by H. And this will give you the frequency of the light that it will absorb. Clear? Now, this expression is commonly known as Bohr's frequency rule. Okay, this expression is known as Bohr's frequency rule, in which we are able to define the frequency of the light that has been absorbed. Now, this same frequency will be, means radiation will be emitted back when it will make a transition back to the ground state. Clear? So when it will make back that transition, again the energy will be released, and that will be the emission lines. Okay, emitted lines, and the initially the one which were absorbed are called the adsorption lines. Clear? Okay. So this is the third postulate. Okay, this is the third postulate. Now we have said that okay, the energy will be conserved. So how it will be conserved? Which energy states are allowed? So this is defined by this formula, which is MVR is equals to NH by 2 pi. So this formula is very, very important. Questions are often asked from this formula. So what we are saying that okay, our energy is quantized. So is a kind of, you can say that momentum is quantized. So first we are trying to quantize the momentum. Once we get the quantized momentum, angular momentum, from that angular momentum we will calculate the energy of that quantized state. Very easy. So how do we calculate the quantized angular momentum? So the formula is, so we know that the angular momentum is given by MVR. We simply multiply it with the radius, mass of the electron, and velocity with which it is moving. We multiply it, and that will be equals to the integral multiple of h by 2 pi. Now this factor is very, very important, known as the Planck's constant. Its value is fixed. It is 6.6 into 10 to the power minus 34. We will encounter this. Now this n that is being given here, that is the energy state that we're talking about. First energy state, second energy state, third energy state. So in this way we are quantizing the angular momentum for a given stationary states. Clear? Okay, so n is what? N is the principal quantum number, and h is the Planck's constant. Now this formula is important in a way that, okay, you can be given that, okay, we have this mass, we have the velocity, just tell that in which orbit the electron is revolving. Okay, in which orbit the electron is revolving. So what we are saying that okay, the electron will revolve in that orbit only where its angular momentum will be equals to the integral multiple of h by 2 pi. Now we call this h by 2 pi is h cut also. So h cut is equals to h by 2 pi. Sometimes we say it as h cut. So if you see this h cut, don't get confused. Just substitute the h by 2 pi there and you will get your thing. Clear? So this is the most important formula, that is defining that, okay, that we are having quantized state. So which type of quantized state? So quantized states are those which are in which we have the angular momentum as nh by 2 pi. Next question, next postulate. So if you are saying that, okay, we are having n is equals to 1, then mvr will be equals to h by 2 pi. N is equals to 2, mvr is equals to h by pi. So these are the allowed orbits. These are the allowed orbits. So there we have just illustrated it, that what is thus n mean. Now this n cannot be fraction. This will be always an integer, 1, 2, 3, 4. So like this, it can never be a fraction. So this thing should be kept in your mind. Now we will talk about, okay, so we have defined that these are the stationary state, this is the velocity, this should be the velocity and all. Now we'll calculate the velocity and all using the electrostatic model. This all formulas have been derived, and we will look at this formula. These formulas are very important. So first of all, we are talking about the velocity, we will talk about the radius, we will talk about, say, energy and all. So let us get started. So this n value, that is 1, 2, 3, 4, this is called as principal quantum number. So first shell, second shell, third shell, fourth shell. So this all comes from this n value that we have seen, and this is the same n we have seen it here in this case, and we have taken as 1 and we have taken as 2. Okay, so coming back to the formulas. So this formulas are very, very important. So for the first formula is the radii of a stationary states are expressed in this way. R is equals to n square by a naught. Okay, R is equal to n square by a naught. This formula is especially for hydrogen only, but if you are taking a much more general formula, then this would be R naught is equals to a naught n square by z. Now this a naught value is fixed, and this is called as Bohr's radius. So this value is basically for the first shell, this 0.5 to 9, and further on the basis of this, we will just calculate the radii of any other orbit that we are talking. Okay, so this is for first shell of the which atom? Of hydrogen atom. Okay, this is radii of the first shell of the hydrogen atom. Now if you have to suppose calculate it for helium, so first shell, but for helium z will be different. Here z is what? Z is the atomic number, and it will be the number of proton and not electron. So that's why we say that, okay, that proton is more basic to or more fundamental to the say atom, because it cannot be changed easily. Clear? So the overall formula is R of the nth radius is given by a naught, which is equals to 0.529 approx accurately, sorry, not accurately, approximately. Okay, 0.529 angstrom. What? 0.529 angstrom into n square by z, where n is the same energy level for which, sorry, same energy stationary state for which we are trying to calculate the radius, and z is the atomic number. Okay, so this z is very important. So here we have not taken the z value because this is for hydrogen. When we take it in common, means the system will be a uni electron, it cannot be multi electron. But okay, we can create ions, na, like He plus or Li2 plus. So in that way we have place this formula. Suppose we are calculating it for the first shell, sorry, the first energy state of, say, lithium. So n is equals to 1. For lithium, z is equals to 3. So 1 by 3 into 0.529, and that will be the radii of the first stationary state of the helium 2 plus species. Sorry, lithium 2 plus species. Is it clear? Is it clear to you? Okay. So this is the radii. Now Okay, the same thing is mentioned, which I have told, that this is the radii of the first stationary state for hydrogen atom, that is 529.9 picometer or 0.529 angstrom. Normally, the electron in the hydrogen atom is found to be in its first orbit. As n will increase, r will also increase. So this is very obvious. So first energy shell will be first in a stationary state will be closer to nucleus. As we move farther and farther, the value of r will go on increasing. Clear? Now we will talk about the energy. So this energy formula is very important. So this all these formulas that we're talking about relating to Bohr's atom. So this all are very important. Why they are important? Because they are asked in the question, and this is value is also in very good accordance with the actual value. You will find that okay, we are just quite good in predicting the energy of the original atom. For that reason, this is very important. Now, so if you are talking about the energy of the first state, or of you can say of the nth state, then the formula is En, means energy of the nth state is equals to minus RH. RH is the Rydberg constant, which is equals to 2.18 into 10 to the power minus 18 joule. Okay, so if you want to calculate the energy in joule, in that case, 1 by n square. N square is what? N square is the again the quantum number or the stationary states whose energy you want to calculate. Clear? Just use this formula, you will find the energy of the nth state. Clear? Next is what? So next they have just put an illustration here. So we have calculated it for different types of atoms. So suppose for helium plus we can calculate, for lithium 2 plus, for barium 3 plus we can calculate the energy value. Now if you want to calculate this energy in terms of electron volt, so what you will do? You will simply multiply this minus 2.18 into 10 to the power minus 18. Sorry, you will divide this by 1.6 into 10 to the power minus 19. Okay, then you will get the energy in terms of electron volt. So what I am saying, that this is the energy in joule. If you want to convert this joule into electron volt, you will divide it by 1.6 into 10 to the power minus 19, and that will give you the energy of the nth shell. Clear? Got it? Okay. So here the formula is z square by n. For radius it was n square by z, and for energy it is z square by n square. Now next, so here what is z? We know that z is the atomic number, so it is 2 for lithium and 3 for beryllium. Now it is evident, so if you just look at this formula, so as we go on increasing the z value, so we are talking about energy, right? So energy has direct relation with the square of the atomic number. So as we increase the atomic number, the energy will increase. Why the energy will increase? Say, so you are saying that you are applying it to hydrogen like species. So as we are increasing Z, we are increasing the proton, but the electron is single because uni-electron system is there. So this is a kind of disbalance you are trying to create, right? So this is getting more and more disbalanced because proton is increasing one by one, and electron is same, and that is disturbing the electron neutrality and hence the stability, right? So we get on increasing energy. Clear? So this is the first thing, that from the formula is evident that as we increase the value of Z, the energy will increase. Now as we move further and further away from from nucleus, that is, if you are increasing the value of n, then you are decreasing the energy value. So why I am saying this? I am saying this because as we are increasing the value of n, we are moving further away from nucleus, because n is equals to 1 will be closer to nucleus, n will equal to 2 will be more further from nucleus, then n is equal to 3 will come, then 4 will come. Now this n is inversely proportional to energy, therefore the energy is what? The energy is decreasing. Clear? Now as we have calculated the energy and the radii, we can similarly calculate the velocity also. We can similarly calculate the velocity also. So let us look at the formula for velocity. Okay, so although the precise equation is not given here, so we can just I am not given the equation here because it is not asked usually. So but if you just want to say quantify, you want to do the qualitative analysis of that, means you want to say that whether it is increasing or decreasing. So it is seen that the velocity of the electron increases with increase of positive charge on the nucleus. So as you are increasing the atomic number and as you will increase the principal quantum number, the velocity will decrease. Clear? Means it is kind of directly proportional to atomic number and inversely proportional to principal quantum number. Now, this Bohr's model is very good in explaining the spectrum. Okay, it is very good in explaining the spectrum. How? See, you have calculated the energy of one orbit. Got it? So for this thing you have done. Now, if you similarly calculate the energy of another orbit, suppose you want to see the you have seen a transition that okay, from this orbit to this orbit the electron is going, right? Now if you want to calculate the energy, what you will do, you will simply calculate the energy of the initial state with the help of formula we have and the energy of the final state, and you will simply subtract that and you will get your what? Transition energy. Clear? So whereas radiation energy, so we are talking about now we'll talk about emission and radiation. So once it will go, it will take energy. So means it will, when it will do a transition from lower to higher, it will take energy, and when it will come back, it will radiate or it will emit energy. Clear? So now let us use the formula. So as I have told you, we can use the formula to calculate the energy. So we know that energy of any state is what? Minus RH by n square. So we are taking here for hydrogen. So Z is taken as 1. So for final state, we can write that, okay, minus RH by n square F, where n square, what is NF? NF is the final state where the electron is going. Minus EI. Ni is the initial state from where the transition is started. So final minus initial. Now that will give you the energy difference. So it is 1 minus initial square minus 1 by final square. Okay. Now we know the value of RH. It is 2.18 into 10 to the power minus 18. If you want to calculate it in, suppose electron volt, just divide this by 1.6 into 10 to the power minus 19. You will get the energy difference between two states in electron volt. Now this formula is very fantastic because it actually explains the experimental value or the experimental data. So without doing any experiment, Bohr just with the help of simple arithmetic formula. So but how did it came to this formula? So I will just give you an idea. So he assumed that the interaction between the electron and the proton is electrostatic. So he used that formula of electrostatic force of attraction, and second formula he used was of angular centripetal force. Okay, we know the centripetal force. So using these two formulas, he combined those two formulas, and with the help of those two formulas, he calculated all of this, say energy, radius, velocity. So he calculated all of this, and you can see that this simple arithmetic calculation has been very accurate with the experimental data, and that is the beauty of this Bohr model. Clear? Okay, so the formula goes in this way: 2.18 into 10 to the power minus 18, 1 by initial n initial square, where n initial is the initial orbit from which the transition is started, minus n 1 by n final square, where n final is the transition state where the electron has gone. Now, as I have told you, can convert it into electron volt. Now, if someone asks you that, okay, this is the energy you are talking about, now just tell me the frequency of light that has been assumed, so that has been consumed. So what you will do in that case, you will simply write delta E is equals to h nu. Okay, you will simply write delta E is equals to h nu. From there, nu can be calculated. Nu will be what? Nu will be equals to this value divided by h, and that will give you the frequency. Now if you want to calculate the lambda further, suppose you want to calculate the wave number, right? Okay, so nu is equals to what? C by lambda. You just bring this C also here. So initially you have brought this h, now bring this C also. So 1 by lambda is what? Wave number. So it will give you the wave number also. Just try this, just divide it by hc. You will get a more you can say defined formula, because often in exams you will be asked not the energy but the wave number or the frequency related to the light that has been absorbed during transition. Clear? Okay. Now, so they have done this thing. Okay, so we have just what we have find. We have find the frequency related to that. So we bring this h here. So what we have done, we have divided both side by h. Okay, I can do it in either way. Either you place h nu here and just cross multiply it here, or you can divide both side by h. So delta E by h will give you nu, and RH by h is giving you, so RH h value is 6.626, as I have told you, in 10 to the power minus 34 joule second. This unit is very important. Always remember this unit. Now RH is 2.18 into 10 to the power minus 18. If you divide this both, you will get the value of frequency in terms of hertz, and here the constant becomes 3.29 into 10 to the power 15. Clear? What does it become? 3.29 into 10 to the power 15. Now, as I have told you, you can calculate the wave number also. Just substitute lambda, nu is equals to, okay, just substitute new value. Okay, you will get this h divided hc. So what we have done, we have again divided this nu by c on both sides. So nu by c is what? Wave number. As I have told you, wave number. And here also divide by c. So hc total is divided by c. So this will give you, so c value is 3 into 10 to the power 8 meter per second. So this will give you 1.09677 into 10 to the power 7. So this is the Rydberg formula. We will encounter this formula. Where does this formula is used? So it is used in the hydrogen spectrum and all. So we will encounter the same formula. So this constant that we are seeing here, this was determined by Rydberg first. Rydberg later on, after Bohr. But this Bohr, this value that has been calculated by Bohr, was it in a very good accordance with the RH that Rydberg calculated with the help of experimental data. So he calculated RH with the help of experiment. And Bohr calculated with the help of just numerical analysis. So here also Bohr has proved that okay, his formula is very good enough. Right? Now, units are very important. Initially, we have the value of energy as joule. If you divide by 1.6 in 10 to the power minus 19, you will get electron volt. If you divide by h, you got hertz. If you divide by c again, you got it at meter inverse. So after dividing by hc, not c, after dividing by hc, we got it as meter inverse. So this value is called as Rydberg constant. Actually, this value is called as Rydberg constant more accurately. Okay. Now, in case of adsorption, means if we are going from a lower energy state to higher energy state, of course, NF will be higher. Okay, NF will be higher. Now, if you're going from, talking about emission spectra, means you're going from a higher energy state to lower energy state, means your initial energy state is having a higher value, whereas the lower energy state will have, the final energy state will have a lower value. Clear? Now, this same expression is also used by Rydberg, as I have told you, to calculate the experimental data. Further, each spectral line, whether in the adsorption or emission, can be associated with a particular transition in the hydrogen atom. Okay, so this is about the transition. So what we will study more about this line spectrum of hydrogen when various lines were given, such as Balmer, Paskin, Brackett, and P Fund and all. So there are various transitions from various stationary states to various other stationary states. Now the brightness or the intensity of the spectral line depends upon the photon or on the same wavelength of the frequency absorbed or emitted. So this is a very important point. We will just use this line again. So when you say that, okay, we are seeing a more brighter light, so that doesn't mean that your light is having more energy. It is just that the light that you are seeing contains a greater number of photons. So that is the reason you are getting a brighter energy. So it is totally dependent upon the density of the photons, right? And not on the energy of the photons. So photons is basically the fundamental particle of light. So that was given by Einstein. So he considers the light as particle, and the particle he named as a photon. Okay. So here I am saying that the brightness or intensity that we encounter is basically due to the number of photons and not due to the energy of photons. Now let us solve a problem first of all. Okay, so we have seen many formulas. So let us just use this formula to encounter some problems. So the first is, what are the frequency and wavelength of a photon that is emitted during a transition from n is equals to 5 state to n is equals to 2 state. So initial state is given. So what we are seeing here, we are seeing a transition from n is equals to 5 to n is equals to 2, and we have to calculate the frequency. Now, never do the mistake of making frequency negative. Arrange in such a order, your formula, arrange the formula in such a order that frequency comes out to be negative. Now your formula is 1 by n initial square minus 1 by 5 f final square. Now, if you put this here, so 1 by n initial square is 1 by 5 square and final square is 1 by 2 square. Means you are putting a greater number on the denominator, you will find that, just analyze it with a little more, you will find that you will get a negative value of frequency. So we will not do that. So for this case, where we are seeing an emission, because we are going from a higher energy to a lower energy. Therefore, in this case, you will subtract how you will subtract 1 by n final square minus 1 by n initial square to get the value of frequency positive. So see, right, we have taken a negative sign against it. So this we have calculated the delta I. So delta I will be negative. Of course, it will be negative. But when we will calculate the frequency, we will not take it as negative. So first we have calculated a delta I. That is 1 by 5 square minus 1 by 2 square. In terms of joule, this value is 2.18 into 10 to the power minus 18. Just put this all and you will get minus 4.58 into 10 to the power minus 19. Why this value is coming in negative? Because the energy is released. So the absolute value is what? 4.58 into 10 to the power minus 19. We will conclude this formula now to calculate the frequency. Clear? So see, we have used this formula. Delta E is equals to h nu. Now delta E value we have calculated. H value we know that 6.26 into 10 to the power minus 34 joule second. So joule gets cancelled out. You will get per second also. Now when you are solving this kind of problem about spectrum and all, just be careful with the unit. Put all the unit, cut the unit and get the final formula more and more accurately. See, we have put joule and joule second here. Joule is getting cancelled. We are getting the final answer in per second. And per second is what? Simply hertz. So this ensures that you are doing the correct thing. Your formula is correct if your dimensional analysis is getting right. Because frequency has a unit of hertz and it is having a unit of hertz here also. So I am not saying that this will work 100%, but at least it will give you a secondary check that you are using the right formula. Okay, so putting all this, we get it as 6.91 into 10 to the power 14 hertz. Now, if we talk about lambda here, so lambda will be C by nu. Okay, lambda will be C by nu. So C value we know here, nu value we have calculated. So you will get it as 434 nanometer. So why they have written 434 nanometer? So it must be coming in this way, like 434 into 10 to the power minus 9. It must be coming 434 into 10 to the power minus 9. So we have just written that in terms of nanometer, rather than writing in terms of meter, we are writing it in terms of nanometer. So this is the wavelength of the light that will be emitted and its frequency will be this much. Clear? Got it? Okay. Now next is we have to calculate the energy that is associated with the first orbit of He plus ion if the radius of this orbit is this much. Okay, what is the radius of this orbit? So what we have to calculate? We have to calculate the energy associated with the first orbit of He plus and plus the radius also. So we have to calculate, suppose we have to calculate this energy in joules. So it is not written here. So if it is not written, then try always to derive your answer in terms of joule, or you can say simply SI unit. So here the formula that will be applied is energy is equals to minus RH Z square by N square. Now here one important thing, take the value of Z as 2. Why? Because we are dealing with helium. So number of proton will be 2. Just take it as 2. We are talking about the first orbit. So N value will be 1. So these things are written here. So this we make mistake here. So in this case, we make mistake that, okay, we take the value of Z because we have the habit of calculating it for hydrogen more often. So sometimes when you get helium or lithium, you just put the habituated value and you get your answer wrong. Okay. And there will be an option that will consider your answer also. And you will say that, okay, we have found the formula, it must be right. So that intuitions come to your mind. So just avoid intuiting in science. Just be practical with it, right? Okay. So we put Z is equals to 2 here. Clear? Z is equals to 2 while we are treating with helium. That is why we are putting Z is equals to 2 and N is equals to 1. And this RH value, that is the Rydberg constant, we take it as 2.18 into 10 to the power minus 18. And that will give you the energy of the first state. It is 8.72 into 10 to the power minus 18 joule is your answer. Clear? Okay. Now second thing what we have to calculate? Second thing we have to calculate the radius. So the formula for radius is 0.529 nanometer n square by z. Means you are calculating the value in nanometer. Clear? So for that we have taken this value, and again we will use the same value of n and z. So n is equals to 1 square and divide by 2. So that will give you 0.02645 nanometer. So hence we have calculated both the energy and your what? And your radius. Clear? Okay. Now every atomic model will have limitations. Now students often complain that why we are reading it, although it has some drawbacks. Each and every theory that you study in chemistry. So unlike your physics, what is the difference between chemistry and physics here? That okay, we have this formula, we will use this formula, it will not change. There is a change, but at a higher level. But in the lower level, we take this formula as granted that okay, this is the formula and we'll use it always. But this is not the case with our chemistry, because there is always a change. The atomic particles are very difficult to study as compared to the macro particles that you see like table, chair and car and all. These particles are very difficult to study. Their nature is totally different from the substance, from the bigger substance or from the macro substance that we see. Okay, so that is very fascinating and at the same time very disturbing. So it is sometimes very disturbing. So it becomes very difficult for the one who is doing the research and all to predict those things, right? So we are getting into all of this model one by one initially so that we can get an idea about how these things are getting developed, right? So in future, if you just able to see this all, then you will be able to appreciate this. So once you see a model that is completely you can say equipped with all the formulas and all the equations that are required to completely define an atom, you will see that okay, this is the formula and all, but you will not be satisfied. So how this came? So for that you have to look back at the history, how we are developing block by block, and we are getting up to the model that we are dealing with right now. Clear? Okay. So coming back to the limitations. So these things are very important for you. So the limitation is that very deep knowledge required to say satisfy this limitation. So I will not go into how these limitations can be removed. I will just tell you the limitation. Okay. So the first limitation is the finer detail. Okay, so we have seen that okay, one stationary state will give one emitted light and that's all. But when this light was, or when this spectra was studied even deeper, you will see that there is a doublet, means those single stationary state is further getting divided, which kind of hinted us that okay, we don't have similar energy in a single stationary state. All electrons will not have the single energy. So that thing was not accounted by the Bohr. So he didn't go deeper into the stationary state. He just stopped there. Clear? And this is this finer detail was observed with the help of sophisticated spectroscopic technique, right? Okay. Now, second thing, the assumption that was made is the limitation of it. We have assumed that we cannot apply it for more than one electron. So that assumption is the limitation, of course, because we can't use it for helium, simple helium like He. Okay, we can't use it for lithium. Okay, we can't use it for a heavier metal, because Bohr's model only accounts for the first interaction that takes place. It does not account for the repulsion that we are getting in multi-electron system between electron and electron. Okay, so we are not dealing with that in case of Bohr. So for that reason, it is not applicable to multi-electron system. So these are the two limitations, right? These are the two limitations. First of all, the splitting of the lines into finer details, which was not observed until we got more sophisticated spectroscopic technique. And second is it is not applicable to unlike hydrogen like species. So these are the two limitations, right? Next limitation is you will find that so when this spectral lines, so when they are exposed to magnetic and electrical field, they again get splitted. Okay, this is the splitting goes on. So you will get, suppose you will get 4 to 5 splitted energy states, and that is also well defined, not that it will get randomly splitted. So that thing will be dealt later on when we will move to quantum mechanics. We will study something about quantum mechanics and we'll study about the quantum numbers and all. Then you will see that why they are getting say splitted. Okay. Next, it does not explain the ability to atoms to form molecules, because we are stuck in hydrogen like species. How we will move to the complex species where atoms are combining and forming molecules? So that thing is completely out of the scope of this theory. Now, all this thing led to the development of a better theory of which is called as quantum mechanics, and that theory was kind of very much advanced, and that uses a new mechanics, because initially the Bohr was using the existing mechanics of Newton electrostatic model. So these are the known mechanics. But what did quantum mechanics does? It takes into account about a new mechanics that is totally unknown to the people, and also unknown to the people those who have invented it. So this is the most funny part of this mechanics, that although the one who has invented it may get confused in quantum mechanics, right? Okay, so they were this mechanic was very good in explaining more and more things, but again, due to the limitations of our say computer system, or you can say the current technology, we cannot get into more deeper aspect of this complex molecule with the help of quantum mechanics also. So this was for today's lecture. If you just look at the important formulas, then I would say the first very important formula is this formula: delta is equals to h nu E2 minus E1 by h. Second important formula is this. So they just ignore this formula, but question may come and you will not get an idea that okay, this question has passed by you and this simple formula was used. Third is this thing, radius of the say hydrogen like species. So this formula is important. Third formula is this formula, which is energy, right? In terms of joule also. If you want, you can get in terms of electron volt also. Then next, this and a transition formula, that what is the energy transition that has been involved, whether in terms of joule, whether in terms of hertz, whether in terms of wave number, that is meter inverse. So this, all these three formulas are important. If you are able to calculate, well and good. If you want to remember the values, remember it, because these are important. Clear? So with this, we have completed the Bohr atomic model. In next class, we will move to hydrogen spectrum. Thank you.